It's a pleasure to introduce our next speaker, Geoff Campbell, and as you can see, it'll be the Rogers-Ramanujan journey from mathematics to physics. Thanks, Geoff.
Thanks, Murray, and I'm very pleased to be talking today, albeit for the circumstances, and Rodney was a good friend of ours, and I appreciated him in many ways. He's a good guy. So about a year ago, I published a book that was on vector partitions, visible points, and Ramanujan functions. And basically, the vector partitions is an area which has not really developed greatly in the literature of mathematical analysis, despite the fact that there's a lot of integer partitions research has been done over the last 100, 200 years. The vector partitions slant on it attracted me because when I did my PhD under Rodney, I discovered something which I've called the visible point vector identities, which in fact are vector partition identities with weights. So in a sense, if you visualize a point in space with integer coordinates and you want to work out the number of partitions, as in like a quiver of arrows, so you give it a quiver of arrows, which is vectors essentially, you can rearrange those vectors in certain ways to get to that point. So the number of possible ways of getting there is your vector partitions to the point. Okay, so in 2 dimensions, it's fairly simple. In 3 dimensions, not as simple, but still not unmanageable. But in 4, 5, 6 dimensions, so on, the mathematics is valid and easy to produce in many cases. However, as you understand, you can't easily visualize what's going on. So in my book, I had to kind of cover a lot of what was already talked about with the integer partitions. And the Rogers-Ramanujan identities was one of the things that really jumped out at me as being relevant. And it was a crossover point between my work and the work of the traditional mathematical analysis in partitions, theory of partitions, and also the work which has been since developed, especially along the lines of integrable systems. And so really in chapter 11 of my book, I actually covered a lot of the adventure and revelations that occurred around about 1980 when Rodney first published his solution to the hard hexagon model. And it was kind of interesting because when I did my PhD, I never really got into a lot of Rodney's mathematics. It was only after I finished my PhD that I started really looking at what he'd done. And I had a growing appreciation over the years of the ingenuity and the beauty of the work which Rodney had achieved. And so in chapter 11 of my book, which I'll just hold up here, got a photograph of Rodney around about 1970. It would have probably been around the time when he solved the 8-vertex model. And anyway, around about 1980, it was interesting because not only did Rodney publish his stuff that was about the Rogers-Ramanujan solution for the exact solution of the hard hexagon model, but within about a year of that, there was an original solution in mathematics that it covered off Farrar's graphs approaches to the Rogers-Ramanujan generalization into higher dimensions. So there was a connection between Rogers-Ramanujan stuff and the high dimensional space vector partitions that I was doing, as well as the fact that I had since started to understand a lot more of what Rodney had achieved. And one of the things which I marveled at was the book which he has, as you know, published long ago, but has so many citations. And if you look at the numbers of citations, it's something like 11,000, I believe. About half of those are mathematics and about half of those are physics. Probably more of them are physics. But, it's an interesting thing that it could have evolved to how it has. The slideshow that I'm presenting today really covers some of what I have in my chapter 11 of my book, but it also brings in the earlier proof that was by mathematicians about the Rogers-Ramanujan identities. In the chapter, I've actually got an abstract now, and I published this as a mathematics archive last year because I believe that having published my 33 volumes of my book, 33 chapters of my book, chapter 11 could kind of get lost in there. Yeah? So I thought probably worth my while to take out chapter 11, which has the Rogers-Ramanujan stuff and Rodney Baxter and George Andrews follow up with it and all of that. And so I put that out there on the archive. But having looked at that since, I realized that there's potential to write new research papers just off that chapter, because at the end of the chapter, I have brought in some work to do with the Q analog of the elliptic gamma function, which many of you may know is an integrable function, and it has been studied over the last 25 years. So that particular function has interesting functional equations. And in the chapter of my book, I actually found a whole bunch of functional equations, not just for the two-dimensional cases, but for 3 and 4 and 5 and any higher dimensional cases. And it involved symmetric functions. Now, the interesting thing about it is I haven't really developed it much further. And those symmetric functions, it may well be that we can apply things like Galois theory and so forth that tells you when the functional equations can exist or not exist, or certain limitations around the algebraic structures that are associated with those functions. Now, I haven't really even had time because I'm working outside. At the moment, I'm working at Toowoomba Regional Council, which is in kind of rural Queensland. So I'm busy working every day, so I don't really have much of a chance to write any research. However, strangely or oddly, even though I haven't worked as a lecturer or a tutor or anything over the last 30, 35 years, and I did my PhD under Rodney, strangely, I've managed to write over 50 research papers. There's 52 or 58, depending on how you look at it. And a lot of people rightly said, okay, they are not peer reviewed. You put them up in the Cornell archive. However, when the book appeared, suddenly 20 of the research papers were absorbed into the chapters of the book, and therefore they are peer reviewed. But that's another story. So if we look at this, Rogers and Ramanujan identities were discovered really by Rogers in 1894. So here they are. And everyone's familiar with those things. The interesting thing about it is that when Rogers first published the proofs of these, he also published the proofs of the continued fractions, which are also given Ramanujan's name, which is an interesting phenomenon because really the Rogers-Ramanujan identities, if I was back then, I would probably say, well, okay, they're the Rogers identities, but they're called Rogers-Ramanujan, which is all right. I'm not sure how that works. And obviously Ramanujan's contribution was significant, and that's how it's settled over time. So here we have it, and you see, Rogers had the proof. And then when Ramanujan sent the letter to Hardy, he didn't have a proof. And then, of course, he found Rogers' paper in 1917, and then they published a joint new proof. And also, of course, Schur was cut off by World War I, and he discovered his own combinatorial proof in Germany in 1917. George Andrews visited ANU around about a year after Rodney first published the solution to the hard hexagon model. And George Andrews was really good at working these Q-series summations out, especially the sums that turn into infinite products. And so he was able to take the 6 regimes of the solution that Rodney had found and turn those into proofs of identities that were similar to the Rogers-Ramanujan identities. A very skillfully done piece of work there by George Andrews. And of course, George is very positive in his appraisal of Rodney. And he once said to me he thought that Rodney was the smartest person he ever knew, which I thought was a very interesting thing for someone like George Andrews to say, because he's seen a lot of people who are probably very gifted and yeah, it was an amazing thing for him to say that. So here, and most of you may be familiar with this, so I haven't gone in a great deal of depth, but in my chapter 11 of the book, I do cover the lattice and the typical arrangement of the particles and the black circles and the triangular lattice and so forth, and how it's split into the regimes. And since there's no more than a third of the points of the total lattice are occupied, the summation that we have up here is equation 1.1. It only covers only a third of the points. So it's an interesting thing. And if we look at it again, you can see what the breakup of the 3 different regimes of the lattice are as configurations. You have different configurations that are possible because of the limitations put upon the charge of the particles. So what Baxter found was that he wanted to calculate the partition function per site of the infinite lattice, and as a function of the positive real variable z, which I've got there on equation 1.2. And following through, he was equipped with his knowledge of how he'd approached the 8 vertex model, and so he was able to represent things in a way which was familiar to him from that perspective. That's how I understand it anyway, not saying that I'm an expert with that. Now, clearly from the mathematical non-physicist's perspective, these diagrams that, were totally a departure from anything that had been worked through in the mathematical analysis, they would have been a nice model anyway, even if there wasn't a physical application. And to have thought of that model would have been a leap of creativity that would have been astounding. But it's, I think, in some ways more astounding that the model occurs in nature and it relates to the adsorption of the helium into graphite, which I think is an incredible thing. It's something that no mathematician who's been working on proofs of Rogers-Ramanujan would have ever probably dreamed could have been true. So it's very interesting. Now, I thought I would just pick up something that was earlier in my book that related to a proof of the Rogers-Ramanujan identities using so-called Durfee squares. And if you look at the diagram here, some of you may be familiar with the Farrar's graphs approach to solving partition problems. And it's a very succinct and almost an intuitive way to arrive at proofs of some of these sorts of partition formulas that would otherwise become kind of involved and algebraically bog people down. However, if you can see a diagram and you can represent the diagram elegantly, then quite often the proof is just involving an intuition and then putting words around the intuition so that it becomes clear to everyone else as well. And there's a gift, of course, in being able to do that. Now, if we look at the Durfee squares representation, which I've got on the slide here, a Durfee square is if you have the arrangement of the array of the partition, which you can see here, the partition of 33, which I've spelled out with the summation, and each row of the partition relates to one of the parts of the partition. If you see the way that it's been broken up into sub-squares, those sub-squares are called successive Durfee squares. Now, it turns out that that those Durfee squares enable one to view the partition in a way which can translate back into an algebraic form. So let's go. It turns out that that particular diagram I had over the page will relate to a proof of something like the Rogers-Ramanujan identities. And here we've got the Durfee squares if you take k successive Durfee squares. So here you've got 1, 2, 3, 4, 5 Durfee squares. And if you have the formula that relates to the number of Durfee squares, it can come out in a way which is like this. Now, clearly in half an hour's talk, we can't go over it. So kind of have to trust that I'm not joshing you guys. Sorry about that, especially the word josh. But you did help me, by the way, Professor. Now, if you look at it, the case where k equals 1 gives you the first Rogers-Ramanujan identity. And there's an actual theorem which Andrews wrote. And the original proof using the Durfee squares was published in 1982. And so that was kind of like a big departure from a lot of what had been done. And over that 85 years, from 1894 or 95 until around about 1980, when Rodney published his work on the hard hexagon model, over that 85 years, a lot of different proofs had been found, but the proofs were not like the Durfee square proof, which is fairly almost intuitive, and also not anything like the hard hexagon model version, which has come up in the Baxter work. It's interesting also that the Baxter type solutions of these sorts of models tends to take the physicist into a different place to where the mathematician would have gone with their partitions. And therefore, I think it's kind of true to say that a lot of the mathematics research subsequent to Rodney Baxter has gone in its own way, and a lot of the physics research has also gone in its own way. However, there are now applications in which I believe there are statistical mechanics publications talking about the integrable systems, which pick up on so-called plane partitions. And the plane partitions are part of my book, of course, because in some sense, a plane partition is like a three-dimensional partition, but it's not. And it's an interesting thing that we can portray some of these things using different models that will be higher dimensional. Sometimes the higher dimensional perspective, despite the fact that you can't visualize it and see it, the symmetries and so forth which arise in the mathematics quite often enable us to arrive at the solutions in an easier way. And in the later chapters of my book, I've published a whole bunch of what they call visible point vector identities. And I've classified as many as I can of the 4-dimensional ones, 5-dimensional ones, and so forth. And many of the identities are kind of counterintuitive. You think they're kind of simple, but they can't be true. Now, when I first met Rodney, it was as a result of George Andrews putting me in contact with him, and I had lunch with Rodney in the city in Canberra. And I showed Rodney some of my visible point vector identities, and he said, well, my first impression is that these must be false. And I said, okay. And then I roughed out the sketch of the proofs, and already they had been published, so they were not false. And he said to me, well, my second impression is that this must be some sort of magic, you know, and that was Rodney's sense of humor. But he was very serious about supporting me, and I'm very grateful for his advice over the years and his guidance. So that's interesting. And I did publish quite a lot of papers, like say 10 papers or something in the 1990s. And then I kind of published a couple intermittently over the years after, but I was not working as a mathematician, so it became awkward to publish. So it's getting close to the time where I've got to wrap up, but if we go through the 6 regimes, okay, people are familiar with this. And the fact that Rodney was able to do the numerical calculations using using his approach with the matrix. He did and his student, they did the right kind of calculation, and they came up with the approximations, and they were able to infer the results. So what Andrews found in 1980 was, for the regime 1, of course, you came out with the 2 Rogers-Ramanujan identities, and that's them, identities 112 and 113. And then for regime 2, it was far more complicated. However, whilst George Andrews was in Australia, he was able to work it through. And so those appear as well in my chapter of the book. So these identities, chapters for the regime 1 and regime 3 appear in my book, and also regime 4, and so on. I was particularly taken by some of the quotations by people. And so in my book, I put this particular quotation that was from Alexander Berkovich and Barry McCoy from University of New York State University. That for about the first 85 years after discovery, interest in the identities and their generalization was confined to mathematicians, and many ingenious proofs came up, and applying combinatorics, basic hypergeometric functions. I remember in looking at the Cambridge Tract of 1935 by Bailey, and it had a proof of the Rogers-Ramanujan identities. It was really kind of convoluted and involved, but it got there. And so we had these sorts of proofs that were verifications, essentially, that didn't tell you much about how that came about. But the Durfee square thing is actually informative, and there are various ways of looking at it that I'm sure will add insight. So the entry of these identities to physics occurred, and what happened was it just, we had the flurry of papers that started at first with Baxter's paper, then Andrews and Baxter and Forrester were involved. Of course, Peter Forrester is now in Melbourne, and he was another PhD student of Rodney. So, and I remembered when I was at La Trobe as a visitor, I was a little while, I was friends with Peter Forrester, a very helpful and insightful person. Then the Kyoto group came up with their things and so forth, and the whole thing is like illuminating for the observer. And there are certainly some mysteries that have come up as a result of this particular joining of mathematical analysis with the statistical mechanics. And I see that it's just not slowing down, as everybody is aware. Now, I think I'm almost at the end of my time. So I really don't have much else I can add to this, other than the fact that I did have some functional equations that I could have produced that I would show you. So these are the, So this is the Q-Pochhammer notation for the elliptic Q-gamma function. And as you can see in my chapter of the book, I've got the functional equations, but the actual definition of the Q-gamma function there is very similar to a generating function for vector partitions. And the generating function for vector partitions has this multi-dimensional functional equation, which I've published in the chapter of the book, which I don't think is in the literature. And it involves symmetric functions. And I haven't really followed this up, but it probably is an area that I could research. And I think I'll leave it on that note. You can see these are the functions that are generating. They're sort of generalizations of the Q binomial theorem, which is well known in the literature, but these are high dimensional versions of it. And I've got the functional equations. So there we go. So that's on that note, I'll end the lecture, and thank you very much.
Thanks, Geoff. Have any questions for Geoff online or in the room? Jean-Marie?
Yeah, among this infinite product and Q series, there are something which is called the mock theta functions.
Yes.
Would you say that these mock theta functions belong to the integrable Young-Baxter world?
I believe, yeah, I think that's true. I think, in fact, that's part of my motivation for wanting to research it. I think that that is true. Yeah.
Okay.
I have a question. Geoff, was there I think I missed maybe a couple of equations there. What is the definition of capital F here?
Oh, here. There we are.
Thank you.
So, yes. So you can see they're multi-dimensional, and they're the source of like a generating function for two-dimensional, three-dimensional, four-dimensional partitions. And as I mentioned earlier, my favorite analogy for those is to take a quiver of arrows, and each arrow being a vector, but with weighted arrows, you know, the arrows could have different weights, all right? Very often, some of my visible point identities give exact results, and it's kind of an unusual thing. And they were not in the literature anywhere. I spent 20 years looking in the literature, and I eventually just thought, well, I'll just publish the book, because I didn't really have a lot of time on my hands to publish a bit at a time. So
what I was wondering was, aren't these related, or at least F1, isn't that also a theta function?
It is, yeah.
Yeah. Okay.
In fact, that's the Q binomial expansion. That particular one is fairly similar to the Q binomial theorem. That's in the Theory of Partitions book by George Andrews, and in fact that particular F1 enables one to easily prove the Jacobi triple product and also the quintuple product as well. You can easily arrive at that. And I would suspect that with the high dimensional examples I have here, you would be able to extend some of those concepts and the ideas. Pretty sure it'd work.
Okay, thanks.
That's okay. Thank you. I appreciate your help before as well.
No worries.
I have a question. Yes, Vladimir?
Geoff, do you have any summation formula, like Spiridonov elliptic beta integral for elliptic gamma function? Maybe you have new summation formulas for your higher functions?
It depends which formulas that you are asking for. I've got a triplication formula.
No, summation formula. You have a product or a ratio like psi 6, for example.
What sort of formula would you be looking at?
Hypergeometric summation formula.
Oh, I'm not really sure about it, but I did have a number of different avenues of approach that I was considering to pursue research upon, and I hadn't really settled on anything. That's why I presented it in that format in the chapter. But yeah, I mean the use of the theta functions and so forth, and there's certainly some loose ends that I'm not really. I don't have the depth of knowledge that you guys might have on this sort of thing, and so I'm kind of putting it out there. But I mean, it may be that what I'm suggesting, it might take some time before we can articulate the best approach to find to extend it the way that it should be done. But I'm not sure. I'm sorry if I'm not I'm not clear about my answer, but yeah.
Fine, Geoff, all good. So thanks for a very fascinating talk. Let's